Okay, so our next talk is going to be open questions for building optimal operation policies for dam management using Factored Markov Decision Processes. And this is work by Alberto Reyes, Pablo Ibargüengoitia, Ines Romero, David Peck, and Monica Boronda.
Yeah, thanks. Well, I'm talking about hydroelectric power generation. So, in an application of MDPs for in this domain. So the agenda is to give a motivation, the related work. I want to explain the problem domain. So I'm going to try to explain the MDP model for dam optimization, how we can get, we can achieve solving this problem in a real world setting. And most important part of this talk is my questions for you, and that's it. So, well, we have, in order to explain it easily, I'm going to give you three main scenarios. One of them is that we have in a hydrological system, we have that a dam can be for different uses, for different functionality. One of them is a reservoir can be used solely for hydroelectric power generation or power or water supply. So the idea is to keep it full, depending in order to. So in another setting, maybe the reservoir could be used solely for downstream control. And the idea is to keep the dam empty. But the problem is when a same dam is used for both purposes. So it is different to operate it. So in consequence, the construction of optimal policies to satisfy both requirements is a complex task. The problem is sometimes even worse, or when during the construction of these policies, there are many people trying to agree about what is going to be the best policy for the management of the dam system. So the problem is that there are many points of views with respect to, for instance, the security or the risks, or maybe the utility that the system can generate. So in all of these things, we have that the problem is how to represent the uncertainty of the rainfall behavior or other meteorological variables, or how to keep the dam operation safe when dealing with the stochastic variables like the rainfall again. So in this work, we want to try to present the three different stages of this work. One of them was to try to state a conceptual model of this stuff and see what happened if the resulting policy was enough or satisfactory, and then try to use reinforcement learning in order to capture samples from the process itself, and try to solve it with more variables in a more complex problem. So we use the framework of factor MDPs, and we combine it with other stuff that I want to talk today. So solving this kind of problems is not new. Actually, there are some guys working on this stuff, particularly these guys. Well, recently they thought that the market decision processes approach could be suitable for this problem. This guy also showed how to deal with the problem using a set of different techniques, and like linear optimization, linear programming, fast optimization, dynamic programming, market processes, stochastic optimization, and other databases approaches. But the problem is, in all the cases, of course, is the concept of dimensionality. So there's a lot of problems together in the same problem. Well, the problem domain, I'm going to try to explain it, to explain it easily. Well, we have a dam, there's a reservoir, and where we have an input of water here coming from the river. The river is streaming from this in this way from this point to this point, and this is an storage device. So we have an input of water, and we could have two outputs of water. One of them is used for power generation. I mean, the flow of water here is used to move a turbine and then generate electricity, or it could be going through this gate, which is an emergency gate. In the case of it cannot control the or cannot keep stable the system, so you have to open this gate also. Or in emergencies, you have to open it. So the goal here in this conceptual model, where I want to have the rainfall, which is an stochastic variable, maybe the flow of water that came across this gate, and this other gate, and the emergency gate. So maybe in this first conceptual model we have the lever discretized in different parts. The idea is to keep the level and depending on the operation of the dam. But in this case, let's think that the optimal level that we want to have is more or less in the middle of the, yeah.
So the optimal level depends on what you want to do with it, right?
Exactly, on the functionality.
The downstream control, you just mean you can buffer extra rainfall?
Yeah, exactly, depending. For instance, if this dam is going to be used for as an storage device, so what you want is to keep it more or less in the yellow part. But if you want the dam is exactly for downstream control, then the green part is better. Yeah. In this case, let's think that we want to use it for downstream control, and we could set the reward function through, around the green part. The problem sometimes is even worse when you don't have only one dam, but when you have more dams connected to along a river, so the problem is more complex. So in a multi-dam system, each power unit and each location are unique with respect to another reservoir, because you can have rainfall here but not here, depending, because there are a big distance among these hydroelectric systems. So in general, the idea is how to build an optimal operation policy for each dam, assuming that each dam is going to be considered as an isolated system first, because otherwise the problem could be huge. Well, I won't say anything about this. I think everybody knows this stuff. But what I think first was that we could take advantage of the factor presentations on the MDP solves that are based on this representation, also in order to try to solve a big problem. So that's why we have chosen these representations. I'm not going to say anything about this. We also represented the transition function as a two-stage patient network and the reward function as a decision tree. In this toy model, but because the first part of the work is a toy model. In the toy model, we discretize the level of the dam in these different colors. I believe there are 4 colors: red, yellow, green, and blue. And each of them was split into 2 parts in order to have over their accuracy. And in total, we only got 24 states. And in order to observe the behavior of the resulting policy. Well, the action space was composed of the joint actions on the different gates in the system. So you could control the input of water and the two outputs of water. So if you could open or close these gates, then the system could behave differently. So they join the different combinations of this. Remember that B0 is the input of water, and B1 is the normal output of water to the turbine, and B2 is the output, the emergency output of water. So in the transition function, I'm just showing here that I'm using the Hugging Expert tool for representing that two-stage patient network, where I have only two variables, the level of the dam and the rainfall as stochastic variables, and we got that the rain in the time T+1 was totally disconnected of the network. So the idea was to instantiate these variables in order to get the transition in the transition state given by the level in the time T+1. The reward function, as you could expect, I worded more the green part because it's what I am interested most in keep it in this part of the dam. So, but the worst case was to keep it totally full. So, and that's why I have penalties for this kind of states. And we have three different rainfall conditions. One of that was no rain. Sorry, I don't know what happened. And when you have a moderate rainfall or an intense or strong rainfall. Actually, I use something like a qualitative representation for taking into account the rainfall. And well, the first results showed that it was what we expected. This on the left, you can see the utility and policy functions. The utilities show with different colors. The light colors are, in this case, and the optimal, the highest value, the highest utility value, and the dark colors are the lowest utility values. So it is difficult to see the behavior of the policy in this image. That's why I included this other graph where this other image where you can see, for instance, that we can get here. The idea is that if we don't have a rainfall, the system is going to converge to the optimal in this part. Because there's no influence of the rain, then there's no problem practically. If you see the rain, always the recommendation is try to do the actions necessary to decrease the level of the dam or increase the level of the dam in order to get this state. When the problem is when there's rain, there's rainfall. Sometimes you could expect that, okay, if you finally are here in this state, the problem is that it is the level. It is going to increase by itself by the rain. So what you need to do in this case is to open some gates in order to decrease the level. And when the rainfall is very strong, practically you have to do nothing when the dam is practically empty. So the rainfall is going to keep it full. Well, the experiments was what we expected. Actually, it was the utility achieved the optimal in two or three steps. And when we tried to solve the whole system in an isolated way, we observed that the utility could be optimal as well. Remember that we didn't solve the problem with the whole system connected or interconnected. It was isolated one by one, having only local optimizations. So it was the first experiment. Then the idea was try to.
Yeah. Are you optimizing them in sequence? First, the most upstream them, and then given the fixed behavior of the next one?
Yeah. One by one, in an isolated way. I mean, I never considered that the actions of one dam could affect others, right?
It was completely isolated.
Yeah, completely isolated.
The policy of an upstream dam at all.
It was but now the challenge was, let's try to solve it. Let's see the complexity of putting all the dams together. So there is here's the problem. So we started with a very simple state space. Then the idea was, let's add some variables, because we were only considering just one dam. And then after that, we have to do a well interpretation in order to have a better resolution in the actions, because some dams can be different in size with respect to others. And then the thing is, okay, we have a very big state space, so now we have to delimitate it. And the worst thing sometimes, at least in this problem, is how you can automatically determine the state transitions or the trajectories that they were mentioned before. Sorry for the image, but the problem of scaling up the problem, the scaling up this process to a real world process is that the complexity can increase to these kind of dimensions. They are huge and practically impossible to solve. It's untractable, these things. Well, at least from a point of view, maybe you have another solution or an idea, but it was totally crazy trying to solve this thing. Well, the whole problem is that the reward function should be oriented to consider different aspects of the problem and not only the utility that you could have in the power generation, right? So there are other problems like I said, risk of security or even some indicators for the energy market stuff. So our reward function should be a weighted joint reward function that could consider different aspects of the problem, but using some weights. So it was an additive function, actually. I don't know if it is okay. It's what so it was the easiest thing that I thought, and it's what I wrote. And I tried to solve the problem with this function. Maybe it could have a more sophisticated reward function, but it worked a bit. Well, anyways, when I had this problem in my hand, so I had to think, because I had a contract with a utility, so and I had only 6 months to finish the project. 6 months. So I have to think quickly and say, okay, what can I do? The first thing I could imagine was I cannot invent, or I cannot invent a transition function, because I am not expert in hydrology. and I don't know how the system behaves, right? So I think that the better thing I can do is use a simulator. So let's try to collect or to get artificial data and try to obtain the trajectories automatically, and I did it using K2, the K2 algorithm, and try to learn a Bayesian, a dynamic, two-stage Bayesian network. Okay, then I introduced here machine learning stuff. Later, well, when I tried to deal with complexity, the first thing I thought is I'm going to buy a supercomputer. It's the only thing I have, but imagine I don't have the space and the infrastructure to put a computer. So it was crazy. But well, I tried to get a supercomputer in another place anyways, but it was impossible. I couldn't have a supercomputer for by another one. So the thing is, let's use more efficient MDP solvers. So, yeah, and about to finish. In the limited exploration space using historical data. So I collected a lot of data from the simulation, but I was matching the samples like that compared with historical data in order to avoid having states that never occurred before, right? In another stuff I thought, but to reduce the problem is I'm going to change the state variables by state functions in order to concentrate some variables, and even the optimality variable. So it is supposed to see here, but anyways, the idea was how to solve it. I thought that the idea could be changed the level by volumes. The volume of water is a variable that is more tractable, because I could have a Euclidean distance or the difference between the desired volume with respect to the real volume I had, and the idea was to try to reduce this distance in each dam, but why not trying to get it, but simultaneously with the rest of the dams in the system. So this was the way the form of my reward function. It was an objective function which was translated into a joint reward function. The way we solved the problem was, okay, let's try to find a policy for the output of the last dam, and keep and simulate the rest of the system. But I'm going to get a policy for only one dam and the output of one dam. Then I use the resulting policy to calculate the optimal policy to the output of the dam, the upper dam, and so on until finish. Yeah. Then what I got were 4 different policies that what I did is I overlapped them in order to have a joint optimal policy. Well, it was like it was difficult to make it, but finally it worked. Sorry, I think in order to see what happened with my model, I tried to write a visualizer. I remember that somebody yesterday was talking about MDP visualizer, where I could follow the trends of each variables in the system. These were got by simulation. So in this case, we have here the objective function, the reward function, the volume, the different volume, the real and the desired volume. In order to try to imagine what is the difference between the desired volume with respect to the real volume. So it was only a way to try to follow the sampling in the simulation. And we also try to test the policy we got, where we can set the different states in the system, which were based on historical data. So the idea is to state an initial state and then try to solve the problem. If you see, we have here the desired volume with respect to the real volume with respect to the desired volume. The idea was try to do this distance tending to 0. Okay. Well, it was a quick visualization that we developed in order to observe the model in it. Then, the results were not bad. Maybe 70% of the cases were successful, but it was not bad because it was an approximation of the model, and it was the first try. Then we tried to build a system with these things and see what happens. I'm not going to put the whole thing in the system, but imagine this implementation in a web system where there's a user. So we had to translate the labels of the policy into recommendations to the user. So here we used a more professional simulator. With the simulator, we could state different scenarios, and based on these scenarios, the idea was try to build a policy. So here, what you have is this is the rainfall, for instance, and this is the level in the dam. This is the level in the dam, and this is the level through a year. To a typical year. So you could have different scenarios and have different recommendations. In this case, for instance, you could have the different dams with different sizes also. And you could have a policy, an optimal policy for each dam. This system was done before I could solve the problem in a joint way, right? So in this system, I'm showing the solution was, the optimal solution was local. Well, the most important thing is, I try to do my best when I face this problem, but I wanted to be here to ask you these questions. And maybe they are open questions that we have to keep in mind because they could be useful for other applications. For instance, how useful could resolve the use of program abstraction or domain transforms in combination with the use of compact representations in AI? Or how to optimize jointly a multiple dam system, in particular for this problem, without losing expressiveness in the representation, but it could be scaled up to other kinds of problems. Or would it be possible to jointly optimize a set of n dams using local solutions? We could take advantage of the first part of the solution when I solve the problem using only local solutions and combine them to find a global one. This is my question. Could reinforcement learning algorithm based on past experiences improve the trade-off exploration versus exploitation in this problem? Like I said, I use historical data in order to guide exploration, right? What benefits can be obtained from related these problems in terms of other kind of multi-agent approaches, like the centralized or the MDPs or the MDPs? Well, I think this is my this is my talk, and my conclusions are, well, I have shown a conceptual model of a real-world application using a tool model. using factored Markov decision processes for dam management, or a complex problem could be modeled compactly using factor representation. I'm totally sure about that. We demonstrated that it is possible to achieve an optimal operation state for a single dam system and a simplified version of a multi-dam system. In the end, I tried to solve the problem in joint way. And I think that's it. So, thanks for your attention.
Any questions?
Yeah, so I think the concept is like you first optimize what the first down does, and then you take into account the second one. Right, because I mean it seems like the influence can only go in one direction, right? The water only flows in one way. Right?
Yeah.
So what you do in the first one,
You mean this problem?
like if you have like next slide, yeah. So if you first optimize the top one and then
Yeah, in the first experiment, is what I did. I actually the order was not important because I solved each dam separately. But in the second experiment, it did because it was a recursive solution. So you solve first this system, you calculated the optimal policy for this output. Then with the optimal policy, you calculated, well, taking into account the rest of the variables in the system. Then later you eliminated this dam, considering that you had the optimal policy for this dam, and I save it for the future. Then I calculated the policy here, considering the rest of the variables, and so on. And in the end, what I did is I overlapped the different policies I got in order to have a joint policy.
So you couldn't separate it completely, right? Because I guess so for the first time, you may need to reason about what it's going to rain at one point.
Yeah.
And the other way around.
no, but that seems like a reasonable approximation.
Yeah.
Yeah, but you're right. Actually, in the first experiment, nobody believed me that it is not going to be useful for anything, right? Because the system doesn't work that way. So your solution is your solution only for your students or something, but not for solving a problem in the real world. So that's why I have to compact the problem in such a way I could to make it more tractable. Is what I tried to do.